Welcome. Chapter 7, Introduction to Econometrics, Stock and Watson. The outline for this chapter is hypothesis testing and confidence interval for a single coefficient, joint hypothesis testing. Why we should not apply t-test on joint hypothesis tests. What happens to level of significance if we do t-test instead of f-test. How can we have some other, for example, equality of two coefficients, then what should we do? What is benchmark model or base model, and why do we need alternative specifications? Why should we not fall in trap of maximizing R square or adjusted R square? What numbers we should report when we are reporting regression results? That is main outline of our course. So far we have, of this video, this lecture, so far we have discussed simple linear regression with one regressor in chapter 4, testing of hypothesis, sampling distribution of slope coefficient, heteroscedasticity, homoscedasticity in chapter 5, omitted variable bias, multicollinearity, imperfect multicollinearity, criteria for including a variable in chapter 6. So those 3 videos are also uploaded. So you can watch those if you are interested. Otherwise, please be with me here. I'll try to explain this outline given here. So for individual coefficients, it's okay. You always have sample statistics here and you go for sample statistics here, and this is your theoretical value divided by standard error of this one. We have discussed that for large sample, its central limit theorem applies and distribution follows normal. Confidence interval as usual, beta 2, beta 3, beta 4, beta k. So each individual coefficient can be tested the same way as we are testing here. No, in case you have chapter 4 minus 2.28, so divided by standard error, so beta 1 hat divided by its standard error, or this coefficient divided by its standard error, this one divided by its standard error. So we see that we can reject t statistics, we can reject this t statistics. So these coefficients are individually significant. Our main topic in this video is joint hypothesis testing. So this I will explain in my next video, how to do it in Stata, how to do it in R. I have also given a link for R codes for replicating all these results. You can watch that. At the moment, my main concern is how can we have joint hypothesis testing? If you remember, our dispute is between educational management and taxpayer. Taxpayer is of the view that student-teacher ratio, expenditure per student, these things have nothing to do with performance of students. Educational superintendent is of the view that class size and expenditure per student and all these things matter. No. Taxpayer claim is that this is zero because these variables are of no use. They have no role to play in performance of students. So our null hypothesis is beta 1 equal to beta 2 equal to 0. Alternative, educational superintendent claim at least one of them is not 0. Either beta 1 is not equal to 0 or beta 2 is not equal to 0, or both of them are not equal to 0. No, why we cannot apply t-test on these models? That's what we are going to discuss here. So H naught beta 1 equal to 0, beta 2 equal to 0, or you may write beta 1 equal to beta 2 equal to 0. Alternative, at least one of them is not 0. So you have two restrictions here because you have set coefficient of two variables equal to 0, q is equal to 2. So the number of coefficients you set equal to some particular value, 0 or some else, that is your number of restrictions. No, why cannot we say if T1 is greater than 1.96, we'll reject H naught, or T2 is greater than 1.96, we'll reject H naught, or both T1 and T2 both greater than 1.96 in absolute values, we'll reject H naught. Why should we not do this instead of applying F test? Why do we need to apply F test? So H naught beta 1 beta 2 equal to 0, this will be rejected if this is greater than this one, or this is, or both. So what happens basically? We have level of significance alpha equal to 5%. When you apply this t test individually and you try to reject this hypothesis, basically you have in mind level of significance 5%, but this level of significance actually has become 9.5%. That's the reason we apply for 9.75%. We see in a while. So you see probability of incorrectly rejecting the null hypothesis using the one at a time. So probability T1 is greater than 1.96, and probability T2 is greater than 1.96. If you expand, so if both are greater than 0, greater than 1.96, hypothesis is rejected. If T1 is greater than, T2 is not, even then rejected. If T1 is less than, T2 is greater than, null hypothesis is still rejected. These are disjoint events. No, these are independent, so therefore you can multiply each, and this is probability of getting more than 1.96 is 0.05, more than 1.96 is 0.05, 0.05, 0.95, 0.95, 0.05, and when you multiply, you add it up, this comes out to be 9.75% level of significance. So your actual level of significance has turned out to be 9.75%, while you are considering 5%. If you make this correction in level of significance, then you can opt this procedure. Otherwise, if you are using 5% level of significance, it means you are committing an error. So so there are two solutions for this. One is Bonferroni method, we are not using it. Another one which is most commonly used, that is F test. What is that F test? That what we are going to see. Again, in F test there are two things. One is homoscedastic only F statistics, another is heteroscedastic F statistics. I'll discuss about these two in a short while. So first of all, you have what is F test? That we are going to discuss. We have an unrestricted model. What is unrestricted model? Unrestricted model is a larger model where all variables are included. So this is claim by the superintendent, and this is a claim by the taxpayer, that these two variables, class size or expenditure per student, has nothing to do, and even this can also be included, but at the moment we are imposing these two restrictions. But you can set all this equal to 0. No. Why this is restricted? Because you see, you have set coefficient of student teacher ratio equal to 0, coefficient of expenditure per student equal to 0. So you have two restrictions, and now you have, after imposing those restrictions, you have a restricted model. From previous videos, from basics of regression, you know that we have more variables here. It means explained sum of square is more here as compared to restricted model, or residual sum of squares in this model is smaller than residual sum of squares in this model, or R square in this model unrestricted will be more than R square from restricted model, because more the number of variables in the model, higher the R square. Now we have to see whether R square from this model and R square from restricted model, whether R square from unrestricted model, R square from restricted model, do they have some significant difference between them? If there is some significant difference between them, it means that restricted model is not a good one, because R square from unrestricted model is quite high. But if there is small difference, it means that beta 1 equal to 0, beta 2 equal to 0. When we impose, there is no explanatory power of these two. That's why R square of restricted model and R square of unrestricted model are very close to each other. But how do we test it? We have F test. R square from unrestricted model, we know it will be more, because you have more number of variables in unrestricted model. R square in restricted model divided by number of restrictions. You have set two coefficients equal to 0, q is equal to 2 here. 1 minus R square unrestricted, this is n minus k. K is number of regressors. If you forget which one here, so please you must have an idea that f is always positive, so higher value will be in first and lower value will be here. Okay, so this is how you can apply F test. If now this F test is greater than critical value, we shall reject null hypothesis that these restrictions, we'll say these restrictions cannot be applied. And if we fail to reject, we will say that we fail to reject that these restrictions, those restrictions hold. Those restrictions may hold. Okay. Many of you may be familiar with slightly different statistics. That's more or less same. That is, F is equal to residual sum of squares. In this case, residual sum of squares of restricted model is, if you replace it by this R square, if you replace this R square by 1 minus residual sum of squares divided by TSS from unrestricted and all that, if you apply it, then you have residual sum of squares minus restricted, residual sum of squares unrestricted divided by Q divided by residual sum of squares unrestricted divided by n minus k minus 1. So these two are exactly same, just a little algebraic manipulation. Let's go. Now, when we have just test score on percentage English learners, our R square is 0.41. When we have unrestricted model, our R square is 0.43. Is this difference large? Is this difference small? We apply F test. R square restricted minus R square unrestricted, Q is equal to 2. When we calculate it, it comes out to be 8.01. And if we use heteroscedastic F test, then it is 5.43. So we don't need to go in this. When we apply a command in stata test student teacher ratio equal to expenditure per student, this basically use this heteroscedastic. If there will be no heteroscedasticity, these two will be same. So safe bet is always use heteroscedastic F test. Similarly, in R package, we use variance covariance sandwich library. I shall explain in next video. I shall do all these empirics in next video using stata and R and maybe GEMOV. So that's what we have discussed. We are not discussing here that what will be the distribution of R square, the F statistics, if you have a lot of heteroscedasticity, whether it follows chi-square or not. We are not going to discuss it at the moment. It may be discussed in some other advanced level course. So what we have discussed so far, that testing coefficient one at a time leads to more rejections than actual, because you are using 5% level of significance, whereas your actual level of significance has changed. So Therefore, it's not good idea to use t-stats until and unless you have adjusted level of significance. So we apply F test. In F test, there are two options. One is heteroscedastic robust F test, and we usually apply this one. And if we apply manually, so this will be homoscedastic only F test. So therefore, be careful when you have heteroscedasticity using Excel. Right? Excel probably has not these type of features built in. So please do these corrections and you check it out. So another way is another possibility. Are you you see testing which one needs to carry out, that beta 1 equal to beta 2. Beta 1 equal to beta 2. Now there are two possibilities. If you are doing it in software, there is no issue. There is no need to transform. If you are just learning it and have to do manually, then you can rearrange beta 1, beta 2 equal to 0, beta 1, beta 2 not equal to 0. So this basically means beta 1 minus beta 2 equal to 0. So therefore you have added and subtracted beta 2 x1. You have added and subtracted beta 2 x1. Now you will have beta 1 beta 2 equal to 0. So this is gamma 1, and here this new variable. So first of all, construct a new variable wi and now regress yi on x1i and wi, and then test h0 gamma 1 equal to 0. That is basically the same as testing this equal to beta 1 equal to beta 2. So therefore you have either way. You can use this transformation, or you can use direct command in stata. Test score is equal to student teacher ratio, expenditure per student. These are the options you can use. Similarly, you can use it in R. We'll discuss all these things in our next video, which will be workshop on these chapter 4, 5, 6 and 7. Okay. No, we have discussed in chapter 6 there are two conditions for including a variable. It should be a determinant of y and it should be correlated with x. And now we are going to discuss what is base specification, what is alternative specifications. Before you go for computing the things, please sit like this way, take pen and paper and discuss what to include, why to include, what should be my variable of control variables. Please remember that variable of interest will remain unchanged. All other variables can be dropped or added in linear form, non-linear form. That's up to you. But main variable of interest, whether class size has an impact on test score, or if I am working on income saving data, whether income has a role in saving or not. All other variables, household size, age of head of household, education of head of household, that will be considered as control variable, but they will not be your main variables. We'll also take that data from Woolrich book on econometrics in our next video on empirical analysis. So please, first of all, you have to consider these things carefully before you go for calculating the things. So specify a base model, specify or benchmark model. So the model which is already existing in theory or whatever is there, that may be considered as benchmark, and what you are trying to improve or what are your suggestions, that those may be considered as alternative specifications with proper theory justification, with rationale, and then you will explain with the help of your results that my model is preferable over the base model or benchmark model. So specify a range of plausible alternative models. Please keep it in mind, true model is never known. True model is never known. So you always need to improve. You can always improve that model. Does a candidate variable, any potential variable, is a candidate variable statistically significant? Use judgment, not a mechanical recipe, please. And don't fall in a trap of maximizing R square. So these are the considerations which you need to keep in mind before you go for calculating the things, before you go to play with data. No, slight digression. High R square means that there is good explanatory power of X variables for Y, nothing more, nothing less, so long as objective is forecasting. 4 objectives: descriptive or summary stats, forecasting, causal analysis, policy analysis. So long as objective is forecasting, it's okay. But otherwise, high R squared does not mean that there is no omitted variable. Bias. High R squared does not mean that your coefficient of interest is unbiased. High R squared does not mean that included variables are statistically significant. No, the variables which we have been discussing throughout these videos: student-teacher ratio, percentage English learners, school expenditure per people, name of the district, percentage eligible for subsidized lunch, free lunch. Why we are including this variable? Because many people assume that parents who are well off, their children have learning opportunities outside class. Or so should we include this variable, or should we include this variable, or should we include both, because they both are measuring income status of parents. So whether student has learning opportunities outside school, that may be linked with your test score, and it may be linked with the class size, because well-off parents would prefer to have their children in small class size. So these two criteria must be satisfied, as we have discussed in chapter 6, to be for a variable to be included in the model. So here you see test score and English learner percentage. In general, there is a negative relationship, that more the number of English learners in a class, lower the test score. In general, students who get reduced price lunch, as this percentage goes up, test score is negatively associated with it. And similarly, income percentage assistance. So again, you have negative association between these two variables. So what should we report in our regression results? Coefficients, the standard errors, measures of it, standard error of regression, R square, number of observations, relevant F statistics, and any other some useful information. Okay, fine, please be with me. I'm just going to wind it up, and that is the final, or you can say climax of these four chapters. 4, 5, 6, 7, yes, 4 chapters. No, the first model which we have discussed was in chapter 4, that is your test score is regressed on class size, intercept, standard error of regression, R bar square, and this one. How we have the results in this nice format, that we also discuss in our next workshop on reproducing all these results in exactly the same way. In similarly, these 5 columns, those will be placed. Second specification. In second specification, chapter 6, we have included percentage English learners, and what do we see? That coefficient decreased to -1.1, more than 100% decrease. Standard error of regression improves, adjusted R square improves. In model 3, we have those percentage eligible for subsidized lunch, that is income status of parents, on the basis of which it is decided whether they will get lunch or not. This is basically affecting test score due to outside learning opportunities. More you can read from the chapter 7 of the book. Okay, this is one thing. So we have included this one, and it has not much difference between coefficient of this one and this one in model 2 and 3. Well, some people have suggested that, okay, why not we should take this as proxy for for parents' income status for learning opportunities outside. Then this is excluded and this is included. Here are standard error of regression. Standard error of regression slightly goes up. R bar square slightly goes down. Now a mechanical way is that you say, oh, model 3 is preferable over model 4, but it all depends upon you whether you are using model 3 or you are using model 4, because there is close tie between the two. So if we look at model 2, 1, 2, 3, 4, in all these models you have significant variables. So when you have included this variable or this variable, it has not only improved standard error of regression and R bar square, these coefficients are significant as well. So we'll prefer model 3 or model 4. If we are forecasting, we may use this one. Otherwise, it may depend which one is considered as better proxy. There is not much difference between the two. No, someone suggested why not include both variables in the model, and in model 5, first variable, second, and these two are simultaneously included. And results are exactly like model 3. What happens? Here this 0.048, this coefficient is not significant, so it means it's redundant. It's an extra variable and it has reduced our degree of freedom. So model 5 is not preferable over model 3 because you have included an additional regressor, but results remain same. So we'll live with model 3, or with some justification you can also live with model 4. So from these 5 models we say that model 3 or model 4 is our choice. And someone may come in chapter 8, we'll discuss, oh, we have ignored non-linearities, so we may have some improvement over these model 3 or model 4. And this is what is the name of the game of a modeling, econometric modeling. So that's all from my side for today. In next video, I am going to replicate chapter 4, 5, 6, 7 results using Stata, using R, and maybe Jamovi in R. Thank you for watching. Take care.